Hello, and welcome to A Gross of Physics. Today is day 42, and what we're going to be looking at is using free-body diagrams to solve problems. Up till now, we've been able to draw a free-body diagram, which is a diagram showing all the forces acting on an object. And what we can do at this point is use that free-body diagram in order to solve for the acceleration or possibly some unknown forces. The key to this, just like any vector problem, is that perpendicular vectors are independent. So what we're going to do is use the horizontal, or the x direction, as one axis, and the vertical, or the y direction, as the second axis. And if we do so, we'll be able to use each axis independently. Now remember our equation for forces. It's F equals ma. But if we have multiple forces, what we're going to have to do is sum them up, and that summation will be equal to ma. For example, if we had a 10 Newton force going to the right on an object and a 2 Newton force going to the left on an object due to friction, well, the net force would be 10 minus 2, or 8 newtons. In that case, the 8 newtons is what we would set equal to the ma term. So if the mass were 2 kilograms, we would have 8 newtons divided by 2 kilograms, and we'd have 4 meters per second squared. So effectively, the free body diagram just gives us a visual representation of just that. It can be more complex, and we'll do problems that have more complexity as we move forward. But if the object moves sideways, you'll have an ma where you'll calculate, in this case, the acceleration to be 4. But then the vertical forces, they're going to cancel out because the car or the object or the cart or whatever is being moved is going to experience no vertical motion during its trip. So that means the table and the gravitational pull, gravity going down and the table pushing up, are going to have to cancel out. So if you were to look at an equation for that, you would say the table going up minus gravity, positive going up, negative going down, equals ma. But then the a term is 0 in that example because it doesn't actually move or accelerate in the vertical direction. Since it's in equilibrium vertically, we don't have to worry about that term. And in that case, what will happen is gravity will be equal to the table force. Now, as far as the problem solving goes, I like to have procedures so that we can follow it through diligently in the beginning, and then as time goes on, you can develop your own nuances to the procedure. But here's how I like to look at every generic free body diagram problem. And of course, different problems will have different nuances, as I just stated. The first thing you're going to want to do is draw your free body diagram. Well, that makes sense. If you're going to use a free body diagram, you need to have one. After that, you may see that you have forces that are at angles. Well, if you have a force at an angle, you're going to need to resolve it into its components, aka you're going to break legs. Now, most of the time we'll have the value of the force. For example, if you're pulling on a wagon, maybe you're pulling it at 20 newtons at 35 degrees to the horizontal. Well, in that case, you'll use sine and cosine to find the x and y components, the legs, of that right triangle. If you don't know the value, you may have to solve for the f later, but remember, you can always say f cosine 35 and f sine 35 if the angle happened to be 35. But that second step is to resolve all the vectors into components, so we just have perpendicular vectors. And then we can get to work solving for whatever unknown we're looking for. At this point, we would sum up all the vectors in the x direction and set it equal to ma. So if there were 5 vectors to the right and 2 vectors to the left, it would be the 5 vectors plus each other, the 2 vectors to the left minus, and then you would set it equal to ma. The mass involved is the mass of the object that the free body diagram is drawn for. When we do more complex problems, you'll see that the mass will be important because different objects may have different masses. And you're going to need to use the m that's related to the object that the free body diagram goes with. So if we were dealing with an object with 2 kilograms, that would be inside the box, and I would know that every time I have an ma term, I would use 2 kilograms. Once you're done with that, you'll solve for whatever unknowns you need to solve for. In the vertical direction, maybe you don't know what the table force is. In the horizontal direction, maybe you don't know the acceleration. But remember, free body diagrams are merely a means to find the acceleration or perhaps the forces that may be unknown in a problem. It's not magic, it's just science. Now, at this point, what I'd like to do is a sample problem. So we're going to bring out the whiteboard, and we're going to look at a problem involving a free body diagram, and we're going to solve for some unknowns dealing with it. So I'll show you a sample problem now. Thank you. On to a practice problem. At this point, we have a car, so I'm just going to draw the box for the car, and it has a mass of 250 kilograms. So I'm just going to write M, 250 kilograms. It experiences a force of 1,000 newtons from the engine, so I'm going to assume the car is moving to the right. I'm going to put E for engine. I'll just spell it out for now, but later we'll just use E equals 1,000. We also have friction from the wind. I'm going to call it FW, which is going to be 150 newtons. And then we have the friction from the tires. I'm going to say F tire, and that is 50 newtons. Now, it doesn't say each tire is 50 newtons. It says the tires. So I'm going to assume that's all of them together. So each one's going to provide 1/4 of 50. What is it, 12.5? 50 divided by 4, 12.5. Assuming it's a car with 4 wheels. Now, this is an incomplete free body diagram at this point. We have the force of gravity down, and we have the force of the ground, F ground. And you'll see the FG and FG is getting confusing already. There's got to be a better way to do this. A little foreshadowing. Now, I want to make sure I know all the numbers for all the forces involved, no matter what the question asks. So I'm going to find the force of gravity. I'm going to do mg. So that's 250 kilograms times 9.8 meters per second squared. So using the calculator, 250 times 9.8, and that'll yield 2450 newtons. Now, the direction of the car is to the right, so I'm going to put acceleration to the right. Doesn't touch the free body diagram because it's not a force, it's an acceleration. So now what I'll do is I'll set up equations. I'm going to start in the y direction because it's one of my unknowns here, and that's going to be F ground, everything going up, minus FG equals MA. Every arrow has a term in the equation, and then you set it equal to MA. So the ground is my unknown, and that is going to equal, well, minus 2450 equals, and what's the actual acceleration up and down? Well, it happens to be 250 kilograms times 0. So the ground is going to equal 2450 newtons. So we have one value already set. Now, that being said, we can then move to the x direction. So sum of the forces in the x equals. And the way the equation is going to set up is you're going to have a different equation because you have different variables. In fact, we have Fe for the engine, minus Fw for the wind, minus F tires for the tires, and that's going to equal Ma. And I'll tell you, at this point, the physics is over, because all you have to do at this point, we have all the numbers, you plug numbers in, 1,000 minus 150 minus 50 equals 250 times A. And our goal in this problem is to find the acceleration. Now, 1,000 minus 200 is 800. 800 divided by 250 gets me 3.2 meters per second squared. So the acceleration of this car is 3.2 meters per second squared. And that's how you find the acceleration. Looks like a lot of work. If someone were to see this work on your paper, they would think you're a genius. But the reality is, you added these two numbers together and set it equal to ma. There was no up and down motion, so that was 0. It simplified. And then in this direction, there were 3 variables: Fe, W, and tires. And the only mistake that I often see students make is they'll say minus Fw plus F tires. They'll add the tires and forget to put parentheses. So I just do a negative for every term going to the left and a positive for every term going to the right. At this point, you could be asked to determine how far along will the car be in 10 seconds if it starts from rest. This would be your A, VI would be 0, T would be 10 seconds, and you could figure out D from that, probably using equation 4. But remember, F equals ma's job or goal is to get you either the F or the acceleration, and then that will allow you to figure out something in the kinematics equations, the big 5. So that's how you do a free body diagram. We'll look at another sample problem in a moment. This problem involves an elephant and a helicopter. So we have the helicopter here. I know, one of the best helicopters you've ever seen. And it's going to be lifting an elephant with a rope. Well, watch this elephant. You thought the helicopter is good. Don't forget the tail. And what will happen is the helicopter is going to lift this elephant, and ultimately the cable is going to break. Now, this is not a free body diagram because what we need to start with is our box. And I'm going to draw a free body diagram for just the elephant. And since my diagrams are pretty weak in most cases, let me put a label on each so at least you know what the two objects are. Now, for the free body diagram, we have the elephant, and we have the mass that goes inside the box. Now we have to determine if the problem gives us the mass or the weight. And it says the elephant has a mass of 1,800, so the word is literally in there, so 1,800 kilograms. Now the forces acting on the elephant. There will be a downward force due to gravity, an upward force due to the cable. So I'm going to say it's the rope, so I'm going to say tension, Ft for tension. Now, if I look at this, there's no other forces involved. There's no sideways motion. It does not mention anything about wind resistance, but it does say that the acceleration is upward at 2.5 meters per second squared. So I'm actually going to write the A 2.5 meters per second squared. Now, I can find the force of gravity. I'm going to start there. mg, 1,800 kilograms, and 9.8 meters per second squared. So using the calculator, 1,800 times 9.8, and I get 17,640 newtons. Now, if this elephant were just resting on the ground, the upward force from the ground would be 17,640. But because the elephant is being lifted by the helicopter, what's going to happen is there's going to be more tension on the rope. It's no different than if you're traveling in an elevator and you accelerate upward. When you accelerate upward, you feel heavier. If you were standing on a scale, you would actually read a bigger value. So as the elevator moves upward and accelerates upward, you will have a larger value on the scale. On the other hand, if the elevator were to move downward, you would feel lighter. And if you want to lose weight quickly, go in an elevator and have the cable cut. You will be weightless for a brief amount of time. Unfortunately, when you hit the ground, you will also be injured. So in this case, what we have is the elephant being pulled upward. So in fact, the tension in that rope is going to be greater than the 17,640. And let's see how that works out. Once we draw the free body diagram, all we have left is to set up an equation. There are no x equations, so sum of the forces in the x equals ma is not applicable. And the sum of the forces in the y direction looks like this. Ft for tension is positive, minus Fg equals ma. Ft is what I'm going to look for, minus 17,640 newtons equals 1,800 times 2.5 meters per second squared. Now, 1,800 times 2.5 yields 4,500 newtons. So Ft minus 17,640 newtons equals 4,500. Bring this 17,640 over, plus 17,640, and we'll end up with the force in the rope is 22,140 newtons. Now, most problems, if this were on an assessment, would probably say something in the beginning of the problem. The maximum tension in the rope is 20,000 newtons. Does the rope break? You know, and what is the actual tension in the rope right before it breaks? So this value here would allow us to be able to determine whether or not the rope breaks in the first place. Now, at this point, we know that the rope breaks. What we're going to then do is calculate the second half of the problem, which is really a kinematics problem in disguise. But what I'll do is reset the board and start with the second half. But this is allowing us to find the tension in the rope, which is the force applied by the helicopter, which is what they ask for in part A. All right, let me reset. All right, now this problem becomes pretty complex because we have the elephant moving upward with the helicopter. The cable's going to break, and then the elephant becomes a projectile and experiences free fall. So what I'm going to look at is two parts to the problem. The elephant moving upward, and then the elephant flying through the air once the cable's broken. So let's just look at, in terms of our first givens list, we'll just call it the up. Now, what I'm going to assume is the elephant was on the ground, so VI is 0 meters per second. We know the acceleration of the helicopter is 2.5 meters per second squared. And we know that the elephant moves 15 meters into the air, so D is 15. And what I'm going to assume is that they had some kind of ground crew here, that the trampoline was removed, the elephant starts moving up, and then they put the trampoline in place just as a precaution. Now, what's going to be important about the elephant's motion is how fast it's moving when it gets to that point, right at 15, when the cable breaks. So what we're looking for is VF. That's our unknown. Now, you could still find T, you could still find just about any other variable, but VF is going to be useful for the next part of the problem. Now, in order to solve for VF, I'm going to use equation 5. VF squared minus VI squared equals 2AD. VF is my unknown, so VF squared, the VI is 0 minus 0, equals 2.5 meters per second squared, and then D is 15 meters. And it's moving upward, so it's a positive 15. So at this point, we only have one unknown, which is VF. 2 times 2.5 times 15. That's going to yield 75, and then I'm going to take the square root, and I'm going to get 8.66. So VF is 8.66 meters per second. And it's positive, so we're going to use the positive root. Now, the beauty of these problems is that the end of one, where the elephant was when the cable broke, becomes the beginning of the next. So we're going to call the givens for the fall. And I don't want to put down only because what is the elephant going to do at the beginning of the problem? Well, if it's moving at 8.66 up, it's actually going to move up a little bit, before it falls down and hits that trampoline. So I'm not going to say it's all up, it's the falling part of the motion. This VF turns into the VI for part 2. And that's a huge concept to grasp. But if you're okay with that at this point, you're doing fine. So what I'm going to say is VI is 8.66 meters per second, and it was positive when it started. Well, now that the helicopter's not involved, it's going to be negative 9.8 meters per second squared. The helicopter was overcoming gravity in order for the elephant to be moving in the first place. Now, the displacement of the elephant goes from this point, goes up a little, but then falls and hits the trampoline, which was 1 meter above the ground. So if you started at 15 and ended at 1, your displacement's actually a negative 14 meters. And that's a tricky variable right there. You have to watch out for the fact that it's negative number 1 and only 14 because of the difference between the start and the end point. Now, of course, the trampoline will bend. It probably breaks because an elephant is probably not going to be held up by a trampoline. However, the scope of our problem ends when we find how fast does the elephant hit the trampoline. So VF is our goal for this one. And oddly, VF was our goal for both parts of the problem. And alternately, the equation we're using is identical as well. We're looking for VF. Now, the VI is 8.66, so we have to put that in, to negative 9.8, and that's times negative 14. So the signs are going to be our biggest concern for this problem. All right, first and foremost, I'm going to do 8.66 squared, and I'm going to get 74.996. The negative stays because it's outside the parentheses. So VF squared minus 74.996 equals, and then you have 2 times 9.8 times 14. We'll worry about the units in a second. I'm sorry, the sign in a second. 274.4. So these two signs make this a positive, and then we had a negative there. So what we have to do is bring the 74 over, but add it to the 274. So I have the 274 in. I'm just going to add plus 74.9956 was the full number. And I have VF squared equals 349.4. Take the square root. Second answer, second square root. Order of operations, second square root, second answer, close parentheses. And I'm left with VF to be 18.7 meters per second. But remember, every time you take a square root, you have a positive and a negative root. And which of the roots will be our velocity? The negative, because we're moving downward. Now, the problem does ask, how fast does it hit the trampoline? So we don't even need to worry about the positive or negative because it's asking for speed, which is the absolute value anyway. So at the end of the day, the helicopter brought it up. It was going 8.66. As it moves up, it's going to be doing a symmetric parabola here. It'll be moving negative 8.66 at this point, and then traveling and gaining another, about 10 meters per second on the way down.